Thank you all for your endurance in this course. So, I guess even the final lecture will be technical. I apologize. But I mean, I guess in this lecture the only slightly non-trivial result is proved. So I want to talk about this Peter-Rosmanian, or more generally Venus and Greenfeld-Rosmanians, but actually I will just say in the end that everything works the same there. So what's this Rosmanian? So this lives over QP, spotty QP. Let this be the functor taking some perfectoid algebra RL plus with an untilde R sharp, which encodes the structure morphism to spotty QP to the set of M in Peter-Rom, what's this R sharp? To the R. R is some fixed integer. This lecture. Is a lattice fold with Peter-Rom plus. Meaning it's a finite projective module of rank R over this ring, such that if you invert the uniformizer, you get this thing here. Okay. And so for a conjugacy class, mu bar of co-characters mu from GM to GLR, which is the same thing as some integers, k1 which equal to kr. We have a corresponding closed Schubert cell. Let's denote this by Rosmanian for Peter-Rom plus or mu bar. So that's a set of all such M with this condition that for all points x, the relative position. So for each point, if this R there happens to be a non-Archimedean field, then there's a complete discrete variation ring. And so it makes sense to talk about the relative position. Peter-Rom plus, I mean, k of x sharp, I should say to be precise, to the R. And I wanted this at most mu bar in the majorization order. So that's some closed Schubert cell. And so the aim of today's lecture is to prove the following theorem.
Is it just like given some kind of reduced structure, or is it something?
It is a functor.
Oh, it's not inside. Okay.
It's a subfunctor of this.
Okay.
Yeah. I mean, everything is reduced for perfectoid spaces anyway. So some of the issue you want to raise that I'm just giving a punctual condition here doesn't. It's not an issue here. So the theorem is that this is a diamond. More precisely, it's quasi-compact, and it's also what I called nice in the lectures, and which was in the meantime changed to spatial. So spatial was called nice before. And it means that the underlying topological space is well behaved. So in particular, it's quasi-separated, but it's more than that. All right. Up for the right. Okay, so in this case, and I guess for many other things where I didn't say this, it actually turns out that the diagonal of this guy is relatively representable. And the closed embedding. Or actually, for the whole guy. Is relatively representable and closed. More precisely, what I want to say and prove is that whenever I have some phenoid space mapping into here, the pullback is represented by another phenoid space, such that the map is topologically a closed embedding. So. Given some until R sharp and two Biedermann plus lattices and 1 and then 2 and Biedermann to the R. Always understood evaluating at R sharp. We want to know that the locus of points where M1 is equal to M2 is closed and represented by a phenoid perfectoid space. Where I should also be saying that this condition here, a priori, what I mean is a set where this happens at any point, but so this will define such a subspace, but then actually on this subspace the two are actually equal as modules over Biedermann plus R sharp globally. So we will show the same for the loci where one is contained in the other. And then the intersection has the same properties. Okay. Okay, so this we do by some kind of induction. So we have the loci where M1 is contained in xi to the minus I and 2, where xi, Biedermann plus, is.
So do we have to know something about the nature of the structure map to know the intersection is still corresponds to a closed subspace rather than some funny thing? This will just come out of the construction.
No, I mean, whenever you have two closed subspaces, the intersection is closed, and also if you have two affine spaces.
Subspaces in the sense of
like
just a map, which is a closed embedding topologically.
Yes. So yeah, it won't be like seriously closed really.
So if you intersect two such maps, it's always.
Well,
is it perfectoid or something?
Yes, so the fiber product of two affinoid spaces is still affinoid, right?
Sure.
And topologically, it's also the fiber product. And so it is this closed subspace which is intersection of the two. Yeah.
Right, with schemes, you would have, of course, could have problems with nilpotent and some residue fields.
Yeah. Nothing like this happens here. Okay, so if I is sufficiently big, this is all of x. Goes there two lattices. So there, some bounded amplitude away from each other, and so we can argue inductively and somehow assume that we already know it about the locus where it's contained some xi to the minus I, and then we wanted to know it for one I lower. And so by induction, we may assume that M1 is already contained in xi inverse M2. Okay. And then the locus where M1 is actually contained in M2, one way to write it is that it's the intersection of the loci over all elements of M1 of the locus where M1 maps to 0 as an element of psi inverse M2 mod M2, where this gadget here is just some finite projective R-sharp module. And again, this has the property that just asking this at all points is the same thing as asking it globally, because an element vanishes at all points if and only if it vanishes as an element of R-sharp. The map to the product of all the residue fields is injective. And so what are we doing here is I'm imposing lots of conditions that elements of R-sharp vanish. So you can write this as a direct summand of some power of R-sharp, and so the condition is that lots of elements of R-sharp vanish. So reduces us to showing that the locus where f is equal to 0 for some is closed and represented by but you can write this locus where it's 0 as so it's clearly closed. Just because it's the complement is the loci where there's at least some number and these are open. And so conversely, we can write this as the intersection of the loci where so pi is any uniformizer, pseudo-uniformizer, and then we can intersect the loci where it's at most some big power of pi. And those are all rational subsets. Thus themselves a phenoid perfectoid. And then the intersection of them is of this form as well. I guess I'm using here that, so what I'm defining here is really a subset of the p-adic spectrum of the untilt, but that's homeomorphic to the p-adic spectrum of R plus, which is X.
So I guess this thing is even pro-étale.
Yeah, I guess any closed subset which is pro-étale in my sense. No, well, is that right? Well, yeah, I don't know. Right. At least it's QPF. But
Can't you do something naive and say, oh, it's representable by R-sharp modulo F?
R-sharp modulo F is not a perfectoid algebra.
It has to be a functor in R.
Yeah, you have to take some sort of perfectoid closure.
Ah, right, there might be no potence there.
Yeah, so actually it is also manifestly, like on the R-sharp level it looks like something heuristically close, but on the tilt it won't at all look like something heuristically closed.
Really? Yeah.
So, I know when you take a perfectoid disk, like this one is on KT, like CPT, and you have the point 1 here somewhere here. And then you can also cover this by Cp T1 over P infinity. Then 1 has lots of preimages, like a ZP verse of preimages. So that's isomorphic to the same space for the tilt. That. So this gadget here is Zariski closed, but this profinite set of points here will tend not to be Zariski closed. So there is no function which vanishes on so many points here. And so the map from, so this ZP many points is clearly also a perfectoid algebra. Just take continuous homomorphism from ZP into CP as the algebra. But the map is not surjective. Okay. Good. So the next thing we want to prove is that these closed Schubert cells are actually closed. So let it. The function which sends a point to the relative position to the standard lattice, so to dominant elements of Z to the R, meaning such sequences K1 through KR. So sending X to the invariant of the lattice at X and beta round plus to the R at X is semi-continuous. And you figure out whether it's lower or upper. I mean, meaning that these guys where impose an inequality are close in there. Okay, so I think you actually have to do some argument here. So essentially what you have to prove is that the locus of such a closed Schubert cell is quasi-compact. That's the essential part you need. And for this it's enough to have something quasi-compact over it. And so there are some things which are easier to see are quasi-compact. Those are the de Maizière resolutions. So we will use de Maizière resolutions to prove this. So, but first let me do some trivial reductions. So we may rescale by a power so we want to show that to fix some U bar corresponding to some K1. Once its locus less or equal to mu bar. And so by rescaling by a power of psi, we may assume that everything is contained in the standard lattice in particular, that last thing here is at least 0. And so then let's consider what one might call a dimension 0 solution. So this lives over this Fn Grassmannian, and so it's a functor which sends R plus with an until sharp to not just one lattice but lots of them. So I don't know. I think there are many ways to phrase this. So the last one will be the standard lattice. And so this kind of thing will be mapped to just as a final lattice in this Fn Grassmannian thing. Where for all I running from 0 to k1 minus 1, I suppose, the modification that you're doing is minuscule. So xi times mi is contained in mi plus 1 is contained in mi. And you're doing some of the minimal things that would eventually produce a modification of this type generically. So, and if you think about it, the condition that you have to impose, I think, is that mi plus mi over mi plus 1 is finite projective over R sharp of rank some j, depending on I, where this is chosen such that it's some of the jump where the k's become greater than I. And so, in other words, we're presenting this modification we're eventually interested in as a successive modification of minuscule modification, like a successive minuscule modification. So.
So something like this is going to be possible for an arbitrary G?
Yeah. Well, anyway, if you want to prove these representability results for Fn Grassmannians, you can usually just embed into GLN and show that it's an enclosed embedding, what you get on Fn Grassmannian. Yeah, anyway, for general G, that's minuscule modifications.
So this you really should do on GLI.
So this you really should do on GLI, yeah. Okay. And then a sublemma is somehow that this gadget here is a quasi-compact diamond, which is actually much easier than. So analyzing the Stemmer-0 solution is much easier than analyzing Fn Grassmannian here. Quasi-compact diamond. It will also be spatial, but I won't prove this. I mean, so what is the structure of the Stemmer-0 resolution? So you can somehow build it successively, where each step you're just parameterizing lattices here up to some step. And so then at the first step, you're just getting a usual affine Grassmannian, parameterizing like usual finite projective modules of some rank inside some trivial model you will just like B1 plus mod psi will just be R sharp to the R. So inside this trivial model, you're parameterizing something. And then at the next step, you somehow have this M1 mod psi, which is now again a finite projective module of rank R, and you're parameterizing some submodel there. And so it's some successive Grassmannian bundle. So by induction, it's enough to prove the following. So if X, say, was by dqp is a quasi-compact diamond, and you have, sorry, I should say this first. So because it lives over SPI dqp, somehow it comes with an untilt, but actually any space over X also has an untilt, because it still has a structure morphism to qp. So you get a sheaf where X sharp on perfectoid spaces over X. And if E over this now characteristic 0 sheaf is locally free of finite rank, then some relative Grassmannian or some dimension D, E living over X is still a QC diamond.
So does the usual argument with power series that the projectivity at the quotient level over R sharp implies a kind of projectivity over B de Rham that just adapts from the power
Yes.
series?
Yes.
Okay.
Okay, and this is something you can just prove. So what does it mean that X is a quasi-compact diamond? It means that there is some relatively representable quasi-profinite surjection. Quasi-profinite. Where we may assume, because of quasi-compacity, that this covers a phenoid. So in general, you can cover any such thing by, like, replace it by some affinoid cover of itself. But then finally, many will already cover X by quasi-compacity. And also, by again replacing it by some open cover, we may assume that if we restrict E to X tilde, that this is trivial.
Yeah, the trivial module over X tilde sharp.
Yeah, so E is isomorphic to X tilde to some rank. But then we can somehow forget about the E and so just replace it by the constant guy. So what we will get is just, so if we take this relative Grassmannian and base change it to this cover, then this will just be somewhat constant Grassmannian dr. Phi product over QP with X tilde.
This I guess is using the sort of descent for vector bundles.
In the isomorphism, not so much probably, but I think in trivializing this E, I probably do. I mean, I need to know that it's.
You're not using it for the. You don't need it to know that this Grassmannian. I mean, to know that this Grassmannian is a reasonable functor in the first place.
I don't think so. Like, I think this identification is purely formal. Like I have to give, like giving a point here, I have to give a morphism to x tilde that I have to do on both sides. And the additional datum is just a d-dimensional finite projective quotient of the trivial bundle of rank R, but that's also the datum I have on both sides. So. And so this gadget here is a diamond associated with some classical rigid space. In particular, also a quasi-compact rigid space because the Grassmannian is projective. So it is itself a quasi-compact diamond. And then the phi product of two such guys is still 1, and so this implies that space extension is a quasi-compact diamond. So it has some further such map going to it from something which is representable. But then the composite map down to the Grassmannian will also be relatively representable, quasi-profinite. So this implies that also it's Grassmannian downstairs. Okay, so that was some of this abstract Emerson resolution, but we were somewhat interested in a specific, I guess I erased it, family of bundles. But now we can look at this Emerson resolution, living over this affine Grassmannian, and we had this bar or plus point of the affine Grassmannian. And we want to know that the locus where this is of relative position at most mu is closed. So this thing lives inside this times over spotty QP. R plus. And so that gadget here will still be a quasi-compact diamond. And because as the diagonal for the affine Grassmannian is closed and representable, this inclusion is also closed and relatively representable. So it's just some pullback of the diagonal. And so this means that the left-hand side is also a quasi-compact diamond. Okay. And now I need a few facts about the de Maizière resolution that are proved in the exact same way as in the classical case. So one is that the image, I guess this is what I will need. So the image of the map from this guy is precisely the set of all x subsets invariant between this modulo at x and B1 plus is at most mu bar. So meaning that, like the fact that you can write it in such a way already bounds that the modifications at most mu, but whenever it is at most mu, you can actually find such a lattice. Also, over the locus where it is equal to mu, it is an isomorphism. And so this way, what I want to say, you could see that the locus, actually in the F-Grassmannian, where the locus is equal to mu bar, so such open Schubert cells, they are diamonds just because the de Maisy resolution is 1. Whereas these closed Schubert cells, over which the de Maisy resolution is now not an isomorphism anymore, there it's not so clear.
So we know something a priori about the nature of this, so this locus is so this locus where it's equal to mu bar is, we haven't proved the closedness we're trying to show yet, so what's the nature
No,
of this
but
locus?
I mean, whenever you have a point, like this is a purely punctual thing you have to prove. And well, one killer argument would be to say that over a point, the beta round plus is actually isomorphic to a power series ring, and then you can reduce it to the usual case there. But that's cheating, but I mean, like the statement is really purely combinatorially. You can really, at the point, you can understand how this works.
You're saying we say it is an isomorphism.
Ah!
As opposed to it is a bijection.
It is about, that's what you mean. No, but again, like, for these spaces, it's always, what do I want to say? So, I want to say that if I have some family where, so assume that this would have be equal to, I don't use this for now. Yeah?
Oh,
I would
okay.
just want to,
Forget. Okay.
like, maybe I'm using the closeness there, but yeah, that's all. Forget about this for the moment. So, so we want to know something about this image here. And so it's certainly quasi-compact because this guy is quasi-compact. You can say slightly more, and I think, strictly speaking, you need this. So the image can also be written as the image of a map from some spar SS plus. Spar plus, where I just, again, cover this guy by some affinoid space. And so this is a spectral map of spectral spaces. And any such map has pro-constructible image, which is something slightly stronger than just saying it's quasi-compact. So where's any image? Also, it is closed under specializations. That's just because the specializations are just the ones which change the R plus, but the functor does not depend on R plus.
All specializations are vertical.
Yeah. And so now the result follows from the following fact that any specializing, meaning closed under specializations, pro-constructible subset of a spectral space is closed. But, I mean, really the only crucial input here into this argument was that we know that's a locus where it's bounded by beam is quasi-compact. Okay. Okay, so now we want to prove that this closed Schubert cell, which we now know is really closed, so again, we may assume that all these ki's are at least 0. And I want to reduce to a very special mu bar, so let capital N be just a direct sum of all of them. And Grassmannian N be around plus just the Grassmannian and this closed Schubert cell for this co-character N000. So then this mu bar will be less than or equal to this gadget here in the modularization order. And so this means that by the closeness we just proved, we can actually reduce to the special closed Schubert cell. Okay. But that one can actually also be described functorially in a nice way. Can be written as all those guys which are contained in the standard lattice, b1 plus to the r, and such that the determinant of them as a subbundle of the determinant of this guy, the determinant of is equal to xi to the n where xi again generates full 1. And it doesn't matter which generator you pick. Okay.
Is this the moment pointwise again?
No, as functors. So it's a functor of all such finite projective modules in there, such that the determinant is equal to this module as sub-modules of discrete RAM. So, but I mean, when you interpret this equality, you should keep in mind that the Grassmannian for GL1 is really just the many points.
I mean, psi, so to speak, is it a variable or is it?
No, I mean, just like I should have said this before, but you have this identification, which follows from the fact that, like, at each point for the GL1 case, you just have the many points in this Grassmannian, but the locus of each of one of them is open and closed by this equality relation I proved. So each one of Like these are really functorially, it's just C many points. And this equality I'm imposing here is just as some equality of 2 points in this Grassmannian here.
So you can check it point by point.
And so you can also check it point by point.
Is it reduced in the Grassmannian?
Well, everything is reduced, it's perfectoid. I should have made this much more clear much earlier. And so in order to get rid of this issue that there is some canonical psi, like on for each input I can choose a psi, but there's no universal one. Let me base change this guy from SPADI QP to SPADI CP. And it's enough to prove that this guy has all the properties we want. And from now on, this psi will be fixed to be p minus p flat. Okay, and so we want to use the following theorem. Assume that we have already proved that it's a fake diamond, which is much easier. So recall that this just means that there is some relatively representable surjection. It might be like a very, very big thing that you have on top of it. Like, you can really trivialize fine projective modules and everything. And then under two small extra assumptions, it will actually be a diamond. And some of the crucial part actually is knowing it's spatial. And I guess I'm using now a slightly different version than I was giving in the lectures. So let me assume that this is relatively representable, the diagonal.
Is this over SPADI QP or nothing?
Or nothing, it doesn't really matter. Because for the analog for QP is relatively representable. Well, this is some of the weaker assumption, it's enough for you. And then this assumption that all the points are not too bad. For x and g there is a QPF map from GT, where this guy's representable, such that x is in the image. Then actually, it's a diamond, meaning there is some map with profiled fibers mapping onto it. So it's, in particular, it has a reasonable Poitov side.
Could something like 2 fail?
Can something like 2 fail? I have no idea. It's a very good question.
Okay.
In the lectures, I was previously giving a slightly different version where I was using something different instead of 1, but the same proof works with this assumption instead. So the other assumption 1 was just used to show that this QPF surjection, or this map with Poitov fibers to D, which we're constructing eventually, is actually relatively representable, but under this assumption, that's automatic. Okay, so in our context, we have already checked this. 2 will also follow easily from the Dimmer zero solution. I will say that in a second. But some of the crucial part actually that remains is to prove that it has these properties. And it's weak, but it's not totally trivial. And so how will we cover this space? We will do it in the following way. Covered by the following x. Let x over spy dcp be the functor which takes some x power plus with some no, I guess I don't even need that. Well, I'll just say what psi is. Okay. The set of all such matrices, over R matrices, in the ring of bit vectors of R plus, such that the determinant of B is in psi to the n times B unit. So psi is a non-zero divisor, so I think this makes sense. So maybe I should say, okay, what am I doing here? So usually you have this affine Grassmannian, and say if you do it just for like something usual, like C power the wrong series T or so, then this has a presentation as the L group of G mod L plus of G, where like L of G of some ring R is G R T, and L plus of G is. And we could try to use such a presentation to show what we want. The issue here is that, so we could also define some kind of L plus G in our Biederam version, where this would be G of Biederam plus. And so that's an inverse limit. Yeah, it's right here. G of Biederam plus mod cos of psi. And each of those, you can show that because Biederam plus mod psi to the I itself is a diamond, those are diamonds. But they are like the affine line, they are extensions of the affine line, and the affine line is not quasi-compact. In this analytic world. And this actually means that this total inverse limit here is something like an infinite dimensional affine space. And an example I gave much earlier in the lectures was that an infinite dimensional affine space actually manifestly doesn't exist as a rigid space or whatever. So it does not exist. That's one issue. But actually we might think that if we want to just understand some closed Schubert-Zahl, we don't really have to go all the way to this all L plus of G, but some finite part is enough. That's actually true, but still it's not quasi-compact. And to check the speciality condition there, you can really only do this if you have quasi-compact covers. And I wasn't able to resolve this in a nice way. And so I did a slightly different realization of the picture. So essentially what I did is, if I have this Biederam plus lattice, then I can extends this to a finite free module over A_inf by this extension of vector bundles business. And then I'm trivializing this thing over A_inf.
Does this this Abhängigkeitsmeinung have an action of some kind of group?
Of course it has. Well, now I mean you can build some slightly more careful versions of this which are okay. But you have to.
I mean, to the open Schubert cells, there are orbits in some sense.
Yeah, as I said, like on the closed Schubert cells, for example, you would still have an action of some quotient of this guy. So on the closed Schubert cells, always factors through some quotient of this. It's just that.
But I mean, how about the whole thing? I mean, in LG, does it exist, so to speak?
Not if you use this functor.
There's no analog of an int group scheme.
Well, there is an analog of an int group scheme, but the issue is just that the open part, which is R plus G, is not even that thing is not a group scheme. I think if you're more careful, you can somehow get around this, but. And so what I will use as a cover is instead this guy, where, like more naively, I could somehow try to do the same thing with p-adic plus here and write any lattice inside there as a translate of the standard lattice under some matrix, which has this property to give the correct relative position. But again, if I would put p-adic plus here, that's like an infinite dimensional affine space, and so it's not good. It's certainly not quasi-compact. And so instead I use this much smaller ring WR plus here, where it will become quasi-compact. So if I consider all B in there, that's an infinite dimensional closed unipole. It's also finite. Perfectoid. Like because we're in characteristic features and only working with perfect rings, it's automatically perfectoid. Okay, so but now we have to impose these conditions, and so these are of the following form. So for an element we first have to impose some divisibility by xi. So the condition that f is congruent 0 mod xi is closed and relatively representable. As it's equivalent to the condition that f sharp is equal to 0, where f sharp is the corresponding element in quad sharp. I mean, so I guess what I'm using is that WR plus mod xi is exactly the plus ring for the tilt, on tilt. Well, that's what I said before, and then the condition that f is invertible is a rational subset, as it's equivalent to the absolute value of f bar being 1, where f bar is f mod p. So we have a map, let's give it some name, lambda, from X to this Grassmannian, or this closed Schubert cell here, which sends any matrix B to translate of the standard lattice speedrun plus to the R under the matrix B. And so because the diagonal is of this space is relatively representable, this is certainly a representable morphism, and we would like to know that it's actually a surjection, and that's true. So lambda is a surjection of sheaves on the facial side. The side of all surjective maps of affinoids. Okay. So let's check for this first over a geometric point. And I guess I do want to allow higher rank points. And so given some m inside of p-adic plus to the r, finite projective, determinant we want to use this to get something over A inf, so, or more precisely over the ring of bit vectors of C++. So that's, except for the fact that I'm working with something of higher rank, that's essentially A inf. So that, let's call this L, is the intersection of M and WR plus inside of C plus. Then L is a WC plus module, such that if you invert psi, what you're getting is just free over WC plus, just because then after inverting M, M becomes isomorphic to this guy.
You don't say isomorphic? And it's not literally equal relative to how M sits inside.
It's literally equal, I think.
It's not just isomorphic.
I mean, it's the intersection of M invert psi and this invert psi inside this gadget invert psi.
Yeah.
But then this is the whole space, and so it becomes equal to this part. And also, if you take L, say invert P, and then complete at psi, this will give back M.
How do you know, for instance, that L is non-zero?
map?
By the first line.
By the first line, by this. Like, I mean, whenever I have an element in here, some sufficient, like, or take an element in WC plus to the R, some sufficiently high psi multiple will land in M, because M is a beta-round plus lattice. And so this will produce lots of elements.
So the fact that C plus is higher rank is not really a problem with this.
No. So I should say that, like in this proof of Fark theorem, where I extended vector bundles from the punctured spectrum to the whole spectrum, that argument didn't really use it as a rank 1 thing, but it worked for any valuation rank. And I didn't realize then that I would need this theorem much later, but I needed it at this point. And so this means that L is finite projected away from the coast point. But now the gluing of vector bundles, and then the extending vector bundles, implies that L actually is itself finite projected. So from the definition of L, it's clear that some of the global sections of its restriction to the punctured spectrum. And so what you can do is you can fix an isomorphism. So because WC plus is local, it's free, so you can trivialize L to WC plus to the R. We get so the transition matrix between this and the standard lattice gives you the matrix. As desired.
The fact that in this particular situation one had to sort of be more attentive to the higher rank points, is this just a general feature of when you're working with a faithful site, or is it somehow in many other situations somehow rank 1 points were enough?
Well, I guess in many situations you really, no, I think like for most of the previous arguments was the case that I was doing some kind of étale sites or some étale covers, and those somehow always extend like are the same over the higher rank point and the rank 1 point, and so I didn't have to do much. But in this case, I'm doing some coherent stuff, and so I have to be slightly more careful. Like say étale stuff usually doesn't matter much, but for the coherent stuff, you want to be more careful. And so, like in general, we can now do some very stupid trick because the faithful site is so big. Then what we can do is we can just map this to the product over all points in the p-adic spectrum of the completion of the algebraic closure of X. So this is a faithful cover.
Countably generated algebras don't do the job.
Yeah, maybe I have to fix some strong limit cardinal also. Over which one has a section.
You can't do something like the W localization precisely because this vector bundle business is
Yeah, maybe I could.
higher.
Maybe, Like, no, it's not so clear actually.
Isn't that a
So
problem?
if you're trying to do this extension of vector bundles thing over a W local base, you run into like I couldn't figure out how to do it.
And this issue that you're now sort of trying to work in a code dimension greater than 2 doesn't seem to be a serious problem. No. I mean, maybe the situation is more special.
Yeah, maybe we can talk about this later. So, I mean, what you would need is a version of this extension of vector bundles over a W local base, and I didn't see how to prove this.
But it's not obviously wrong.
It's not obviously wrong, I guess, no.
I'm not sure if the ERC, not algebraic electron.
I don't think my proof used this. I think this algebraic closeness is just in the step before, in step 2 in my proof.
Oh, yes.
Yeah, here it's just
Yeah.
screwing up.
You have no problem with
Okay, and so I guess an immediate corollary of this is that this is a quasi-compact vector. However, it's not clear that the underlying topological space is well behaved. What we like being spatial meant that this has many quasi-compact open subfunctors. And yeah, it's not clear how to produce them, but so the condition that guaranteed this was that the map from the relation to x back again is open. So let's consider the relation we have to impose. So let x be this fiber product over Cpx. Sorry, over the Grassmannian. And so this sets close and relatively representable. This fiber product. And so thus it's itself a finite perfectoid. And something that for lack of better notation I will call L plus G, although I mean maybe it's what you should use as L plus GLR here. It certainly maps to the other guy. Let's say it's a 1 over Cp, which takes some RR plus to GLR of the bit vectors of R plus. So this maps to GLR of beta 1 plus, C on tilde. But it's really much smaller.
When you say here that closed relative representable, hence affinoid perfectoid, I mean, we're really.
I mean, are you using that?
Using the fact that the diagonal is kind of an affinoid.
Yeah. Because I gave this example that infinite morphisms in general are not so well behaved. I try to avoid this notion of infinite morphism, but anyway. And so this L plus GLR is certainly also affinoid.
What does this arrow mean?
I just want to say that there is a map from this further to this other guy.
I mean, your L plus GLR it exists by itself. It's not even 500 over SPCP.
It exists by itself, yeah. But I want a version like
where R has to live.
Yeah, where R has to live with by ECP. Because otherwise it's not a finite perfectoid.
Ah, right. Without that base, it's not representable.
Yeah. And so what I will need is that so certainly you can change B by some element of GLR, and you don't change the map to the Grassmannian. So this means that there is a map to Y here by the action, and this action in Grassmann. Something that I probably should have said before is that the width vectors of R plus actually map injectively into the speed around plus guy, which you can check on the geometric point.
R sharp.
R sharp, yes, I think. That's fine. Like everything here is somewhat implicitly as an untilt, because I'm always working with a QP. So what do we have to show? We have to show that if you have two matrices B1 and B2, in X, if they give the same point of the affine Grassmannian, then their ratio, which a priori is an element just in GLR, well, I want to say it's a priori just in Peter of R sharp. Well, it certainly lives there. But what we want is that it actually lies in this integral subring. Maybe it's also a priori clear that we just have to invert psi here, because the determinant is a multiple of psi up to unit. And so this can actually be checked on geometric points of higher rank. And there it just follows from the uniqueness of this lattice L constructed. Because this lattice L, it's like there's a unique finite projective WR plus module, which somewhere outside of the special point does the correct thing. And this has to be preserved by this gadget. So in some sense, this X here is torser under this group here, at least on the faithful side. And so that's some kind of replacement of this presentation as LG mod L plus G. So I think the orbits of this group are still the same as for the bigger one. Although I haven't thought about it, but I think it's true. Okay. And so now we can actually finally verify that this Grassmannian over from spatial. So this was automatic if the map from this relation y back to the covering x is open. Or it's, I mean, don't, like, it could be spatial without this being true, but like the only way we can check that something is spatial, at least that I know, is to produce some faithful cover where the relation has this property. But how does this work? So y was just this product with all plus GLR, which was open, if you want, in x times an infinite dimensional ball. Oh, I mean, just embed GLR into R by R matrices. And so this projects to x. And so this is open.
And are we arguing here on the level of topological spaces only?
Yeah. Just, I mean, and well, I mean, what I said so far is like true without topological spaces put there, but what I want to prove is just on topological spaces.
What is infinite dimensional unipole? What is that?
It's just the p-adic spectrum of CP flat, and then you put x more, like infinitely many of those. And so this is open. And so one way to see this is that you can write all of these things as inverse limits, like of this of finite dimensional closed unit balls, this of perfections of rigid spaces with CP flat. And so this way you reduce to showing that if f prime from y prime to x prime is a flat map of rigid spaces. So reduce to rigid spaces. Then it's open. Which actually uses formal models, I think. But okay. So to finish the proof, that this guy is, well, we already have compact and spatial, but we still need that it's not just a fake diamond, but a diamond. We need to check this punctual criterion.
So in this passage to the limit, you use some generalization criterion with constructible sets to check openness is inherited in the limit?
Now, like whenever I have an open subset, quasi-compact open subset, say here, then it comes by a pull from some finite level. And the transition maps to the finite level is also surjective because we're just taking product space. X system is X. This is GPF. It's X in the image. But this can actually be deduced from the De Mazur resolution.
Give it to you for all x at once?
No.
Okay.
No, like each x is contained in a unique stratum where the relative position is equal to mu, and for this part, the dimensional resolution for this corresponding mu
Okay. So
is
for
an
each strata,
isomorphism.
you just have to-
Yeah, so a priori, some of the dimensional resolution shows you that each of the open strata are not too bad. But like to get the closed strata, you need some. I couldn't see any simple argument. And the good thing about this criterion for fake diamonds to be diamonds is that as soon as you know they're spatial, the rest is something punctual, and with this it's enough to know that some stratification is good. Okay, and I guess I'm mostly out of time, so let me just conclude by saying that with the same proof, one shows that the Sprains and Greenfeld-Grassmannian I was introducing last time, or also in this talk on Monday, essentially, which lives over any number of copies of ZP minus a closed point. And maybe also has some varying bounds on the type of modification we allow. Is a quasi-compact spatial document. Great. So that's the end of my course.